The highest velocity in the converging nozzle is limited to sonic velocity because more than that, the flow is choked, right? You cannot get any higher velocity. So what you can do to increase the velocity is you attach a divergent part, okay, a divergent section on that thing. And this is the one that I told you. Single of it is the one that you see the figure. 3 point something meter, and for the Saturn it has 1, 2, 3, 4, 5, 6. Anything else not counted yet? Okay, not including the booster, because if you look at the rocket to send someone there, usually you will have one big one, right, and then another small attached to that, right? When you first see it lit off, usually the booster is the one that is turned on. The booster. So why they do that is because when you have that, now relative velocity between this one is zero, relatively. But if you look at the absolute velocity, now it is moving at a very fast velocity, right? Now when you're still moving and this one, the second one, take off, right? It blasts off. Mean now the velocity is between this and this, right? Which means now this velocity is already high. This velocity is even higher. So that's why you get stages. The reason is that action, reaction, force, and relativity. Okay, relativity theory. Okay. Now, if you want to reach supersonic velocities, you need to attach a diverging nozzle into that part. Okay. Okay. Now, similarly, we do that, but now we have a converging, diverging nozzle. So rather than having those only there, it will be like that. Okay? Same concept. We start with the pressure 0 equal to PB, or P0 equal to PB, or P1 equal to P2. When P1 is equal to P2, you can see there is no flow. So the pressure is constant along the nozzle. No flow, no pressure different. Okay. Now, if you lower the pressure, when you lower the pressure, okay, when you lower the pressure, the flow is start. So you can see the pressure is decreasing because you have a converging part, right? You have a converging part. What will happen? Velocity will, come on, the holiday is still tomorrow. Eh? The velocity will increase, the pressure will decrease. The velocity increase, pressure decrease. Then you have a diverging. A diverging because you haven't reached a supersonic flow. So when the velocity decrease, the pressure increase. Simple, yeah? Now, you reduce it further until the throat reaching the P star. When the throat reaches the P star, what happens? You get a sonic flow, right? At the throat. Okay? So when you reduce the back pressure further, you will reach a sonic flow in the throat, but the difference in pressure is not enough to maintain the sonic flow. So when it reaches the diverging part, it's going back into subsonic region. So even though you already reached the sonic flow, if you do not maintain the pressure, it will go up again. Which means your pressure will increase, your velocity will decrease. Okay? If you reduce it further, if you reduce the back pressure, you reduce here, the pressure here. Right? when you reduce it further, then you will reach a sonic flow and supersonic flow in the region, in the converging part. You will reach a supersonic flow nicely, then suddenly the ex-girlfriend of your boyfriend came. Now you get a normal shock. It's abnormal shock. Huh? You get a normal shock, then what happens? When you get a normal shock, the velocity decreases rapidly, which means the pressure will increase rapidly. Okay? The pressure will increase rapidly, the velocity will decrease rapidly. So at the outlet, rather than having a supersonic flow, you will have subsonic flow. Even though in this divergent part, in the diverging section, you already reached the supersonic flow. So you have reached sonic, supersonic, but suddenly normal shock occur and then it becomes the subsonic again. So how to maintain the supersonic? You reduce it even further until it will push the normal shock outside of your nozzle. If you reduce the back pressure further, you will have outlet supersonic flow. Okay? Okay? If you do not do it enough, then you will push the normal shock into the outlet, but you do not limit it. You do not you do not eliminate it. Then it will become the oblique shock, and it is more complicated than the normal shock. Why is coming back here? Virus. You put virus here. Lucky I don't put my thumb there. Okay, so those oblique shock will occur. Okay. Now this one, please go on your own. This is the problem example. You can see here I compare the result based on my calculation, my own calculation, with the one in the table. Now you can see if I do the calculation, I got 0.5283, exactly the same with here, 0.5283. Same goes for the density, 0.666339. The thing that I need to remind you is be careful with the unit. Okay, that's why in all my calculation I maintain the unit, because then I know what to do with it. If it is kilojoule, I need to convert it into joule. If it is kilopascal, I need to convert it into pascal. If it is megapascal, you know how to convert it into pascal. Okay?
But then in test, they use the table or?
As I told you, if you get K is equal to 1.4 and somehow your Mach number is exactly the same as those in the table. Let's say you get air 2.4, then you can use the table. But then if you are having air but the Mach number is 2.68, you cannot use the table anymore. Because interpolation will not give you a good result. Remember that. Okay, interpolation will not do good in this case. Right? Because your interpolation is linear while the calculation is not linear at all. Okay, so now for the shock wave, the normal shock wave, why we call it normal? Because of the shape. It is normal to the flow of the gas inside the nozzle. Whereas oblique is the one that you see if you have an airplane. This is the oblique shock wave. Okay, what is the consequence of the shock wave is that your flow is no more isentropic, which means P naught is not constant anymore. Your rho naught is not constant anymore. The only thing that remains is T naught. Why T naught constant? Because it comes from the conservation of energy. Energy cannot be created nor destroyed. Okay, so you cannot do that. That's why you got it equal to right? You get HO1 equal to HO2, right? And then if in the isentropic flow your entropy is 0, in this case it is not 0. Okay? If you look at the book, it is not discussed in our class. You will have the so-called Funnel line and Rayleigh line. Okay, you need to learn it on your own. You may need it later on when you are working. Okay, it will not be there in your exam, but not necessarily that if it is not in your exam, you do not learn it. Okay, right? You may need it. You may need it. So, one of our objective in mechanical engineering program is to make you as a lifelong learner. So of course, we want you to learn even though you already grade B, right? You always learn. Learn how to become a good husband. Learn how to become a good father. Learn how to become a good son. Learn how to become a good lecturer. I'm still learning, right? You learn how to become a good student, how to become a good citizen, right? You're still learning, right? You say that when you graduate, you are not learning. You're still learning. Yeah? You learn how to raise your kids. You learn how to teach them. And it's the hardest part of your life. Right? So lifelong learning is there. Anyway, for the normal shock wave, we will use this equation all the time, as you will see in our tutorial later. Okay? So with that, actually we have summed up all the compressible flow nicely. Okay, if you want, we can slightly recap it on the next Tuesday. Okay?